There we go. Okay, so what we're looking for here, it looks like you guys did a great job. We're looking for a vector W1 that will survive this matrix, but will not survive this matrix. Now, in class last week, and in some of the homework problems, it turns out that this last matrix that you get here is like all zeros. Okay, if this matrix is all zeros, then of course every vector is going to get killed by it. So in that case, you only have to worry about making sure that your vector is not killed here. So remember, the idea here is, so a minus lambda I, W1 should not be 0, but a minus lambda I squared W1 is 0. That's what we're looking for. Now, in this problem, it turns out that the a minus lambda I squared is not 0. So we have to choose a vector that's going to get killed by this matrix. So for example, the vector 0, 1, 0 for the vector 0, 1, 0 would not be a good choice. Because if I do the calculation here, I'm not going to get the 0 vector. But you guys did the right thing. You chose 1, 0, 0. Okay? And 1, 0, 0, of course, the nice thing about using something like 1, 0, 0 is when you do the multiplication, you just pick off the first column, right? Okay, that's easy. And this is, I think I talked about this on the video as well. So you just get the first column, and then when I put 1, 0, 0 here, again, I just pick off the first column, and I see that, yeah, I got killed. But if I had used 0, 1, 0, then instead of picking off first columns, I would be picking off second columns, which wouldn't be good here because I would be getting not the 0 vector, you see? So you do have to be a little careful. If this matrix is all, if this matrix is all zeros, then you don't have to worry so much because you know that whatever you do, you're going to be fine. But this matrix, in this case, was not all 0, and so I had to choose W1 very, very carefully. So I see you guys have a couple of different choices here. So here's a vector for W1. Let me just point this out. 2, 0, 1. If I choose W1 to be 2, 0, 1, then when I multiply this matrix times 2, 0, 1, I don't think we did this right. We're going to get 0, 0, 0. Why is that?
Why did you do that wrong?
Well, why is it not going to work? By the way, please don't. This is something else that's really going to bother me. Don't write the matrix on the right of the vector. The vector is always on the right of the matrix. I can't even. It doesn't make sense to take the vector unless you're going to write your vectors as rows instead of columns. You can't do that. So anyway, it's all right. No worries. So my point here is that if you choose W1 to actually be an eigenvector, notice what our original eigenvector was, 2, 0, 1. If you did that, then that vector is going to die right away. Then that's not good. We want the vector to not die when we hit it with the first matrix. So we don't want to do this one. Sorry. This one, though, is great. This is great. Let W1 be 1, 0, 0. When you apply the matrix to it, right, A times W1 is going to give you -2, 0, -1. By the way, that's not the same eigenvector that we wrote down earlier, but it is a multiple of it. And so it's all right. Okay, so this is actually an eigenvector, so that can be W2. And it does get killed by the square of the matrix. So my second solution, let's go ahead and just use that. The second solution then would be 1, 0, 0 plus t times -2, 0, -1. That make sense? All right with that? So I have my first solution and my second solution, and we don't have any exponentials there because the lambda was 0. The lambda was 0. Okay, so that's the solution. Now we have another eigenvalue. What was the the other eigenvalue?
-1.
-1, okay, good. So with -1, this one's a little easier. So let me just put it here. I'm going to look for the null space of the matrix that I get when I add 1 to the main diagonal. So if I add 1 to the main diagonal, I'm going to get this. Adding 1 to the main diagonal. I just get that. And I just have to do my EROs on this thing. Let's just multiply the first row through by a -1. I'm going to put the all 0 row at the bottom. And then I'm just going to add the 1, 1, -4 to the -1, -3, 3. And that's going to give me 0, -2, and -1. I'm doing this kind of quickly. I'm trying to not belabor the details of the calculations that are old. So this is basically a row echelon form. Close enough. Okay? So what's my free variable? Okay, and so z would be equal to what? T, alright? And then if I do that, then if I solve for y, what will I get? -1/2 of t, good. Okay, now I gotta solve for x. I'm gonna have to write this out. So x plus y minus 4z is equal to 0. So x is equal to 4z minus y. 4z minus y if I solve for x, right? And that becomes 4t plus 1/2 t. So that should be 9/2 t. 4.5 t. Okay, so if I extract my, if I bust out my t, I'm going to get 9/2, -1/2, and 1. Okay, so we have that. No need to do any w vectors on this part. Okay, so my third solution in my list is going to be e to the -t times that vector, 9/2, -1/2, and 1. And so I can get my general solution. Here. General solution, which would be x of t equals, so I've circled, I'm now circling, all 3 of the parts to the solution. So it should be C1 times 201 plus C2 times the vector 1, 0, 0 plus t times -2, 0, -1. Right? And then plus C3 times e to the -t times 9/2, -1/2, and 1. That's the general solution. Everybody see how I'm getting that? Just putting the 3 parts together. It's kind of a big problem. We're doing a lot of big problems. Now are we done? Oh, why are we not done?
Initial value.
Oh, I threw something different at you here and I gave you an initial condition. So the initial condition is going to help me to do what?
Figure out your constant.
Find my constants, which are C1, C2, and C3. Exactly. Okay, so let's plug in 0 for t into our general solution and see what the calculation gives me. So we may not show all of our steps on this just to save a little time, but at least want to show you kind of how it will look when you write it out. So x of 0, if I plug 0 in for t into everywhere I see a t here, what am I going to have? I'm going to have C1 times 201 plus C2 times 100, very good. And then plus C3 times 9/2, -1/2, and 1. And all of that should be equal to whatever they gave us over there, which which was -2, 1, and 1. There we go.
So can we multiply that third vector out by 2?
Yeah, you could.
It'd be the same thing.
Mhm.
Okay.
Yeah, you certainly could do that. Okay, so this is going to be 3 equations and 3 unknowns. Yeah.
In doing so, you can only do it with one.
You can what?
You can do that with just one piece of that, right?
Well, you could multiply this. He just wants to change this vector. He doesn't like using 9 halves, -1 half, and 1. So he wants to change it to 9, -1, 2. Perfectly safe thing to do, and he can do it with just this one. You can do it with this one too if you want. You can change 1, 0, 0 to 29, 0, 0 if you want. There's nothing wrong with that. Basically, these constants allow you that flexibility. Okay, so I'm just going to leave it the way it is. This gives you 3 equations. So the first, if I go across the top row, I have 2c1 plus c2 plus 9 halves of c3 equals -2. The second row is kind of helpful because there's no c1, no c2. -1 half of c3 is equal to 1. And on the bottom row, c1 plus c3 is equal to 1. You guys, of course, can solve that as a matrix system if you want. This one is very simple, though, at this point, because the second equation tells you that c3 is -2. You can immediately get that. And if c3 is -2, then what else can you figure out pretty easily? Yeah, so what will c1 be? Good, c1 will equal 3. So c1 is equal to 3. So this is going to be 6 plus c2 minus 9 equals -2. So can anybody tell me what c2 is? 6 plus c2 minus 9 equals -2. So what is the solution? Just 1, yeah, good. Okay, so c2 is 1. So among this family of all of these solutions that are in the general solution, the one specific one that we have found that solves the initial condition would be this one. So basically it would be 3 times 201, 3 times 201, and then plus 100 plus t times -2, 0, -1, and then c3 is -2. So -2 e to the -t times 9 half, -1 half, and 1. Okay. So that's the specific solution that matches the initial condition. Question?
Up there, you didn't use the t part though when you're solving for the initial condition for the constant?
Well, what happens is you plug in 0 for t.
Oh, right, and then that
So
one.
yeah, so if you put
Okay.
0 for t here, right,
Right.
so all the t's get
Sounds good.
they kind of disappear there. Okay, I feel pretty good about that. Problem 5 on the review sheet, as it turns out, is, I'm just looking at the time. Problem 5 on the review sheet, actually we did it in the group work on Wednesday, so I think I'll skip that one. Which means at this point I've done all of them except number 1, number 2, and number 6. And I guess part of number 6 was also in the group work. So let me do the problem 1 on this sheet. I'm going to do a slightly theoretical problem, just to make sure you guys know I probably will ask you something that's more theoretical. So I'll give you an idea what kind of thing that might be. On the quiz, I didn't really give you many theoretical problems. It's all just very number crunching oriented. So, but for the test, I probably will try to give you something more theoretical. So we'll do this one as number 5. Suppose that a cubed, so this is a matrix, a cubed minus 2a squared plus 4a plus 5i is 0. Okay. If lambda is an eigenvalue of a, show, it's like doing a proof, doing it proof. So if lambda is an eigenvalue of that matrix, what you're going to do is you're going to show that lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is also equal to 0. Okay, and this is actually always true. If there's any equations that a matrix satisfies, turns out it's interesting, its eigenvalues satisfy the same exact equation. So this is kind of a funny result. So it's something that you kind of study in general in Math 307, but for here we're just doing a very specific. So, maybe you have an idea how are we going to look at this? Oh, good. So exactly right. If lambda is an eigenvalue of A, I already know bells go off right away. That means A of E equals lambda V. Exactly. So for some, this is my solution. So for some eigenvector V, we have AV equals lambda V. I mean, the reason why that makes sense to use that is because basically you're saying that the A does the same thing that the lambda does. AV is the same as lambda V. So the A and the lambda are kind of comparable, and that's kind of what this is about. You're trying to say whatever is true about A also works for lambda. So it makes sense that this has something to do with it. Okay. So from this equation, does anybody have a suggestion as to like what we could do from here? Done?
Multiply.
Have you already looked at the solution?
Oh my goodness.
Okay. As long as you didn't, that's fine. Go ahead.
You can multiply given matrix part by V.
This one?
Yeah.
Oh, okay, sure. So of course I can multiply both sides by V. Yeah, I think that's not a bad thing to do. So also, we have A cubed. Tell me if this is the wrong thing. I think this is what you are telling me. I take that matrix times V, and it should be 0 times V. Is that what you mean? What is 0 times V going to be better? 0. Okay, good. Now that's the 0 vector. All right. And why did you want me to do that? And how does that help us? Okay, I'm going to distribute the V on the left side. Very good. So I have A cubed V minus 2A squared V plus 4AV plus 5IV adds up to the 0 vector. Okay? Anybody see anything we can simplify on that? Okay, substituting. What can I do as far as substituting? So AV becomes lambda V, right? So I see it right here. By the way, I times V is going to be what? V. I is a matrix times the vector V gives me just V again, right? It's like multiplying by 1. Okay, so this is really 5V right here. What we have here is, I'm kind of working backwards, I guess. So right here we have 4AV, but we can change that to 4 lambda V, right? 4 lambda V. Okay. What about these first few terms? Yeah, so maybe just as a little side calculation here, what would A squared V be? I just want to work out how we could simplify that. So that's A times V, right? And if I kind of think of it one matrix at a time, right? That might be helpful because AV can be changed to what? Lambda V. So we have the A on the outside, and then we have lambda and then V. And what can I maybe do there?
The lambda equals the front because it's constant.
Great, so I put the lambda outside, and then I have AV again, and so then what?
That's lambda.
AV is another lambda V, so it becomes lambda squared V, right? Everybody see that? So A squared V is the same as lambda squared V. And I won't show you all the steps right now, but I'm just going to say similarly, a cubed V is equal to lambda cubed V. Same exact calculation, basically. Does that make sense? So a cubed V, I'm going to change that to lambda cubed V. And this is minus 2 lambda squared V. Okay, so this is what we have. And of course, what I'm trying to show is right here. So does anybody have an advice for me on what to do with this? Say again?
The vector.
Right, the V can be pulled back out again, right? The V can be pulled back out again. So I get lambda cubed minus 2 lambda squared plus 4 lambda plus 5. Okay, now what? Divide by V. When's the last time you divided by a vector? Don't want to do that. Can't divide by a vector. Did you just cross it off? Yeah, crossing off the V is like dividing by it.
Multiply by,
There's no reciprocal of a vector either. Huh? Oh, it can't be done. I can't divide by V, but think about this with me for a second. First of all, an eigenvector. What do you know about an eigenvector? Remember the definition? The definition of an eigenvector. Of course, this equation is true, but what else has to be true about an eigenvector? It has a pair with the eigenvalue, which we have, which is lambda. It's in the null space of A minus lambda I, which is what this is saying. But I'm thinking of something else. This is A minus lambda I of V is equal to 0. But an eigenvector of a matrix must be, fill in the blank. One word. Okay, it must be that's for a matrix. I'm talking about for an eigenvector. An eigenvector must be non-zero. Eigenvectors cannot be 0. Remember that? So I said that here. V is an eigenvector. It automatically means it's not 0. So look what you've done here, guys. You've taken a non-zero vector. You've stretched it by some constant, and it's become 0. So what must that constant have been? 0, right? You killed your vector. This is not 0 to begin with. You multiplied it by a number, and it became 0. So that number, which is what's over here, must be 0. Okay, that's the reason. That's really the reason. Okay, so from here, what you would want to say is, since V is not 0, I'm kind of running short on room here, but I'll squeeze it in. Since V is not 0, lambda cubed minus 2 lambda squared plus 4 lambda plus 5 is 0. That's the idea. Okay? Really not too bad of a little problem there. But that's how it works. Okay with that? We'll give you a couple more. If you have to go, it's fine. I'm going to keep talking for a little longer because I didn't finish my sheet yet. But I understand you guys might have things to do. But I'll just keep talking. Probably if you all leave, I'll still keep talking. Yeah, that's right. Keep that thing rolling. I think I might skip number 2 for now. I just want to, so you guys know how to do like these phase portraits, right? Maybe I don't need to review it because we just covered it recently. What I'm talking about is sources, sinks, and saddles, spiraling in and out, and circles for the 2x2 linear systems.
You gave us a pretty good chart, so I think if we review the chart, we should.
Yeah, I mean, there's a lot of, there's the group work that we did on Wednesday, has a couple of examples in it. Yeah, I don't think I really need to focus too much on that. Let me just give you a couple more, because I guess I'm up to number 6 here. Let me just give you a couple of practice problems on going back to the higher order differential equations for a second. So let's suppose I ask you to find the general solution. And let me give you the equation here. There's like 6 parts to this problem. I'm not going to do all 6 parts, I'll just do some of them. So let's do a couple of the parts here. So the first one I'm going to do is y double prime minus 8y prime plus 17y equals e to the 4x times the cosecant of x. So I want you to think about where in the material is this problem coming from. Anybody know? Okay, the annihilator section. Do you know how to annihilate e to the 4x times the cosecant? I know you maybe don't have your table in front of you right now.
No.
I will give you the table for the test, but does anybody off the top of their head know anything about annihilating that?
No.
You know, cosecant of x is just the reciprocal of sine of x. So it's actually a fraction. It wasn't written as a fraction, but this is really a fraction. Anytime you're trying to annihilate a fraction, you're in for a tough ride, right? It's very hard because the derivative of a fraction is going to use a quotient rule, which is a complicated formula. It usually makes things worse, not better, right? So annihilating this is going to be tough. In addition to that, this order of this differential equation is what?
Second.
Only 2, right? Second order. So what easy out have we learned? If we can't annihilate the function, but it's only a second order differential equation, what else have I taught you to do?
Variation.
Variation of parameters, right? What he said. Yeah, exactly. So it's this 3-step process, variation of parameters. So that's how we're going to do this. And I just want to practice it. We'll go through it pretty quickly, okay? So what's the first step? Auxiliary equation. What's the auxiliary equation?
R squared minus 8R.
Awesome. Okay, so we get this thing, and this does not factor nicely, of course. It's a kind of a messy expression. So how am I going to get my roots?
Quadratic.
Make sure you know your quadratic equation. Okay, you'd be surprised at the things that people get hung up on. So the quadratic equation is going to be 8 plus or minus the square root of 8 squared, which is 64, minus 4ac. 17 times 4 turned out to be 68, all over 2. Okay, and I can split that up as an 8 over 2, plus or minus, and then this is the square root of negative 4, which would be what? 2 times I, and then I'm dividing by 2, so just I. Okay, so 4 plus or minus I. Based on that, does anybody know how to write down? So the first step after you get this done is to write down the complementary function. Right, so this should be pretty easy points on the test if everybody just knows how to write these down. Go ahead, Bastian.
1 e to the 4x cosine of x
Okay.
times sine of x.
No. Plus.
That's already
Plus-
your,
plus
that's
sine.
your whole first term, right?
Right.
So then what's the second term?
Oh, okay. C 2 e to the 4x times sine of x.
That's right. Okay, so it's 2 separate terms. 2 separate terms. Okay, so we have that. That's the complementary function. Okay, and what do I need to do now to start working on the second step?
Get your y1 and y2.
Okay, you need to use the variation of parameters method, which means you have to have the y1 and the y2. So does everybody remember, well, before we go any further, let's just write them down. What would you want to use here for y1 and y2?